Now let us study the second method, that is a factorization method to evaluate the limits. In the limits of the type limit of f of x upon g of x when x tends to a, if we get f of a equal to 0 and g of a equal to 0, then the direct evaluation fails. But we can factorize f of x and g of x because each has the factor x minus a. So on cancelling that, the limit can be directly evaluated. So this means that suppose we have to find the limit of a rational function, which is a polynomial upon another polynomial, right? Now when we put x equal to a directly, and if we get numerator at 0 as well as denominator at 0, then it would mean that x minus a is a factor of both numerator as well as denominator, correct? So therefore we try to factorize numerator and denominator and cancel out the factor of x minus a, so that whatever is the remaining portion, that can be directly evaluated by putting x equal to a. Alright, so that is how we find out the limit using factorization. Now let us solve some examples based on this method. Here we have to find the limit of x square minus 1 upon x minus 1 as x tends to 1. Now if you observe, by putting x equal to 1 directly, we will get 1 minus 1 whole upon 1 minus 1. So that gives us 0 by 0 form, which is meaningless. So therefore let us see the factorization method. Now you must have easily figured out that the numerator can be factorized as x plus 1 and x minus 1, whereas denominator is already x minus 1. Okay, so what we can do is we can cancel out the factor of x minus 1, and therefore what remains to find the limit of is x plus 1 as x tends to 1. So therefore here we can now directly evaluate the limit as 1 plus 1, which is equal to 2. Alright, now one point to note here is that while we cancel out x minus 1 without bothering much, we have to remember that cancelling a factor means we are actually dividing numerator and denominator by x minus 1, and whenever we divide, we must ensure that that divisor cannot be 0. Okay, so here we have to justify that x minus 1 is not 0, right? How to do that? So look here, we are given that x tends to 1, that means x is approaching 1, it's going closer and closer to 1. So remember that x has not become 1 yet, it is just in process. So therefore x has not become equal to 1. So therefore if x is not equal to 1, then of course x minus 1 is not equal to 0. Right? So this particular expression is definitely not 0. Therefore we can cancel or divide by x minus 1. So this point is to be kept in mind wherever we divide by a particular factor throughout the chapter of limits. Okay, now let's go ahead and see one more example. Here we observe that limit is to be found of once again a rational function where numerator and denominator both are quadratic expressions. Now we can easily factorize the quadratic expressions as x minus 5 and x minus 4 in the numerator, whereas the denominator is nothing but x minus 5 into x minus 1. Right? So we cancel out the factor of x minus 5. So what remains is to find the limit of x minus 4 upon x minus 1 as x tends to 5. Now since we have already removed the troublemaking factor, we can now directly evaluate the limit. So that is 5 minus 4 upon 5 minus 1, so which is 1 upon 4. Right? That is the limit. So moving on, let us see one more sum. Now here we have a cubic expression in numerator as well as denominator. we can still verify that if we put x equal to 2, we will get a 0 by 0 form. Alright. So this proves that x minus 2 is guaranteedly a factor of numerator as well as denominator. So we must find out the other factor, right? Because we'll have to divide it and get the other factor. So that means we have to write the numerator as x minus 2 into something divided by denominator also is x minus 2 into something. Now since both are cubic polynomials, the remaining two factors that we have to find out will be obviously the quadratic factors. So how to do that? For that we have to divide the cubic polynomial by x minus 2, and which we do by synthetic division, right? For that we must write down the coefficients of all descending powers of x, right? So starting with the highest power, we have the first coefficient as 1. So I write 1 here, then write 3, then minus 9 and minus 2. Alright. Then on the left side we write the value by which we have to do the division. So 2 into 1 we write in the next column, then 3 plus 2 is 5, then 5 into 2 is 10, minus 9 plus 10 is 1, and then 2 into 1 is 2, and minus 2 plus 2 is 0, which means the remainder is 0, and which we anyways knew even before doing the division. So the other factor is nothing but the expression denoted by these three indicators. So therefore this is nothing but the algebraic form of x square plus 5x plus 1, which is the required other quadratic factor in the numerator. So that is x square plus 5x plus 1, right? Now let us divide denominator also by x minus 2. Now if you observe, in the denominator the quadratic term is missing, so its coefficient is 0. So we write the remaining coefficients and complete the synthetic division as before. Once again we get 0 remainder, and here the quotient is having coefficients 1, 2, 3, so that stands for it is x square plus 2x plus 3. Right. So that is what we write in the denominator. So that is x square plus 2x plus 3. So here also we cancel out now the factor of x minus 2, and in the remaining expression now we can directly put x equal to 2, and that can be calculated even orally. So 2 square is 4 plus 2 5s are 10 plus 1, and in the denominator we have 2 square 4 plus 2 2s are 4 plus finally 3. So that gives us numerator is 15 and denominator becomes 11. So that is the limit. So this is how we use the factorization method.